Hello everyone, welcome to the second episode of the AtCoder Chronicles, where I'll be explaining the first 6 problems from AtCoder Beginner Contest number 370. So the first problem is called Raise Both Hands. A person raises a combination of their hands. If they do not raise exactly one of their hands, print invalid. If they raise only the left, print yes. Otherwise, if they raise only the right hand, print no. So as with most first problems in these contests, just do whatever it says, simulate it, and you'll be fine. Problem B is called binary alchemy. You're given an integer n and a triangular array of element transformations A. There are n elements called element 1, element 2, all the way to element n, and combining elements I and j results in this element I'm writing here. Find the result when combining element 1 with the elements 1 to n in order. So again, you do exactly what it says, you simulate it, and it's not that difficult. Problem C is called word ladder, and you're given 2 lowercase strings s and t which are the same length. You can repeatedly change a character of s until s is equal to t in the minimum amount of changes possible. And you have to ensure that the intermediate strings are in the minimum dictionary order. So for example, AAA is before AAB in the dictionary order, and AAB is before ABA in dictionary order. Since in dictionary order you prioritize minimizing the characters near the beginning, first decrease all the characters that need to be decreased from left to right, and then increase all characters that need to be increased from right to left. Problem D is called cross explosion, and if you played the game Bomberman, then it's quite similar to it. There's an H times W grid full of walls with an area of no more than 400,000 cells. However, we don't know exactly how wide or tall the grid is, so we'll use a dynamic data structure to store it. Then, Q bombs at given positions will be detonated in order. If a bomb is detonated in the cell with the wall will explode. Otherwise, the 4 closest walls horizontally and vertically will explode, if they exist. At the end, print the number of walls remaining. So, the number of bombs is quite great, it can be up to 200,000. So if we went through the entire row and column of each bomb to see which walls we need to explode, the time complexity for each query would be OH plus W, which is way too large because you're multiplying by Q. So this calls for a clever use of data structures. The ideal one that we're going to use is the set, which we can make use of the standard lower and upper bound functions to find the walls that we need to explode in logarithmic time, and also carry out the deletions in logarithmic time. So if you don't remember, the lower bound returns an iterator to the first value greater than or equal to the target, and the upper bound returns an iterator to the first value greater than the target. This means we need to be careful and explode the previous element from the lower bound, but we can keep the upper bound as it is. Problem E is called avoid K partition. You're given an integer array A of length n, and you're asked how many ways there are to partition the array such that no partition has sum equal to K. This seems like a dynamic programming problem because we can add the partitions onto each other separately. So let dpi be the number of solutions for the first I elements. So we start with dp0 equals 1. We can easily write an inefficient O(n) cubed solution to this problem. Have 2 nested loops for I and j representing the endpoints of a single partition, then add up the elements from j plus 1 to I, and if this isn't equal to k, then we can add dpj to dpi. This can be easily optimized to O(n) squared by using a prefix sum on A to skip the adding up, which will be equal to sum I minus sum j. Now we need to optimize this further, and this is a bit difficult. And the key is that noticing that sum I is constant for the inner loop. So we need only avoid adding the dp from the positions where sum j is equal to sum I minus k. This can be done efficiently by having a map mp, which keeps track of the dp sums for each value of the prefix array. Finally, we can create a variable tot, which totals the sum of the dp so far. Our answer will be this tot, subtract whatever we need to subtract, and the solution takes O n log n with the map, which is fast enough. The answers can be very large, so we'll have to take them with modulo, but be very careful where you use it. In particular, don't use it on the prefix sum of a, as some values may be negative.